Hi guys, good morning. Okay, in this class we are going to move another topic, that is a truss element and derivation of element stiffness matrix for same, that is a truss element. Okay, so this syllabus. Okay, so what do you mean by truss element? So truss element is nothing but what? It is an engineering structure, okay, made up of a number of small bars connected by a means of welded joint, okay, or any bolts or rivets, pin, etc. is called as truss element. Okay, okay, is called as truss element. I shown in this diagram. So many different types of truss element will be there. Okay, what do you mean by truss element? Truss is nothing but it is a engineering structure, okay, made up of small numbers, okay, small bars. Okay, so 1 2 3 4, okay, these are the bars, okay, which is connected to by a welded joints or rivet joints, pin, whatever that. Okay, so such type of element we are going to call as truss element. Okay, so in present day, nowadays, where you are going to use means, so mobile tower. Okay, best example is mobile tower. Okay, so mobile tower is connected what? A small bars. Okay, so that is a best example for truss element. Okay, so what do you mean by truss? So truss is nothing but what? It is an engineering structure made up of a number of bars connected by a means of welded joints or bolts, rivets, pin, etc. is called as a truss element. Okay, example is mobile tower. These are the different types of truss element will be there. Okay, so look at, these are the small bars. Okay, so this is what, this is a different types of element, this is a different types of truss element. Okay, so this is called as truss element. Okay, so again, trusses are classified into two types, that is a plane truss, that is called as 2D truss, and space truss, that is called as a 3D truss. Okay, a plane truss is nothing but it is a truss in which the one which satisfied the below equation, that is this equation should be satisfied, that is m is equal to 2j minus 3. Okay, so m nothing but what? Number of bars, j nothing but number of joints here. Okay, so that is consider for example this example. Okay, so this is the element. Okay, so how many, bars will be there in this? Okay, so here uh, 1 2 3 4 5 6 7 join, that is 7 bar will be there. So 7, okay, 7 number of bar. Okay, so have to, whether we have to check this. Okay, with the help of this formula, m is equal to 2j minus 3. So m is equal to number of bars, j is nothing but number of joints. Okay, so j, how many joints will be there? So this is 1 2 3 4 5. Okay, 5 joints will be there. So 2 into 5 minus 3, 10 minus 3, which is equal to 7. Okay, so like that we have to satisfy this equation. Okay, so this is the load acting. Okay, here that is a load. And one more thing is, in the truss element, load should be applied at node only. Okay, wherever nodes are there only we are going to apply the node. Okay, so this is about the 2D truss element. Okay, next one is what are the assumptions made in truss element. Okay, so in a truss element, a force can be only applied at the nodes only, nodes or joint. Okay, so look at, this is the load 1 2 3. Okay, due to force applied, the force should be either tensile or compression. Okay, so these are the two forces should be act on this truss element. Okay, third one is the joint in a truss are associated with a frictionless pin joint, and the fourth one is the self weight of the bar of a truss are neglected in a compression or to the external load applied. Okay, these are the four assumptions are made in the truss element, and this is most important question. What do you mean by truss element and what are the assumptions made in truss element? They may ask you in the examination. Okay, around 4 mark question. Okay, so next is how to, that is a coordinate system. Okay, so how to denote the truss element in local coordinate and global coordinate system. Okay, in local coordinate it looks like a 1D element, in global coordinate it looks like a 2D element. Okay, so you look at here, this is an element. Okay, so this is node number 1, node number 2, this q1 dash is the displacement at node number 1, q2 dash is the displacement at node number 2, and whereas coming to the global coordinate, each node having 2 degree of freedom along x and y. So at node number 1, 2 degree of freedom will be there, q1 q2, at node number 2, q3 q4, 2 degree of freedom will be there. Okay, so this is the difference between local coordinate and global coordinate system. Okay, in local coordinate system, orientation should along with the this length of the element. Okay, whereas here not like that. Okay, so each node you are having 2 degree of freedom in. Okay, with the help of this we are going to calculate the next question, that is a derivation of element stiffness matrix for truss element. Okay, so this is most important derivation, so anytime examination they ask. Okay, so question is derive an expression for element stiffness matrix of a truss element. Okay, how we derived the bar element, same how to derive the truss element. Okay, so figure A shows the local coordinate system, figure B shows what, this is global coordinate system. Okay, so this is what figure B shows the global coordinate system. Okay, so here A 192, this is the element. So in the local coordinate system, the axis is along the orientation is along the axis of the truss element, whereas here not, it is 2-dimensional object, that is x and y will be there. Okay, so look at this, this is the element 192. Okay, q1, this is what, from if you displace this position it will changes. Okay, so from here to here the length will be what, q1, and here to here length will be what, q3. Okay, so here from this position to the changed position going to consider length is cos theta, and from this to this element is this length is what, q2. Okay, and from this to this q1 dash, and from this to this q2 sin theta and q1. Okay, so that is q1 and q2. Similarly, how to take the this q3 and q4 at node number 2. Okay, same way. So how you got this? Okay, so now with the help of this diagram you need to calculate the derivation of element stiffness matrix. Okay, so in the local coordinate system, let q1 dash and q2 dash be the axial displacement at node number 1 and 2. Okay, and q1 dash be the element displacement matrix. Then we are going to take this. Okay, q dash is equal to q1 dash into, that is q2 dash. Okay, transpose of q1 dash q2 dash. Okay, so give equation number 1. This is in the local coordinate system, since only one displacement will be present at each node. Okay, well, coming to the global coordinate system, each node having 2 degree of freedom. At node number 1 q1 q2, at node number 2 q3 q4. Okay, so like that you have to write q is the element displacement. Okay, in global coordinate system, give equation number 2. Okay, so the relationship between the q and q dash is obtained by referring the diagram, so that you have to simplify this equation by observing the diagram. So q1 dash is equal to q1 cos theta plus q2 sin theta, give equation number 3. q2 dash, which is equal to q3 cos theta plus q4 sin theta, give equation number 4. Okay, let us assume L be the cos theta and M be the sin theta. These are called as the direction cosines. Okay, substitute these in this equation 3 and 4. So you got the modified equation as q1 dash, which is equal to L q1 plus M q2, and q dash, which is equal to L q3 plus M q4. Okay, give equation number 5. Okay, so the same you have to write in the matrix form. You are going to get like this: q1 dash and q2 dash, which is equal to Lm 0 0 0 0 Lm, and these are the displacement q1 q2 q3 q4. If you multiply this, means you are going to get same this value, that is equation 5. Okay, so give equation number 6. Again, just to modify, that is q1 q dash is, let us assume this one is a q dash and this one is a L, and this one nothing but q. Okay, so where L is equal to Lm 0 0 0 0 Lm, this is called as a transformation matrix. Okay, so give equation number 8. Okay, to find the direction cosines, that is L and M, consider a small element strip. Okay, so here node number 1 and node number 2 in global coordinate system. Okay, so here at point 1 x1 y1, at this point x2 y2 will be there. So length, just to extend this length, make a triangle one. So this length is x2 minus x1, and this length is y2 minus y1. Okay, so L is equal to cos theta. Apply the cos theta definition. Cos theta definition is what? Adjacent by hypotenuse, that is x2 minus x1 by Le, and same as n sin theta, that is opposite by hypotenuse. So you have to substitute the definition values here. So you are going to get L is equal to cos theta is equal to x2 minus x1 by Le, M is equal to sin theta, y2 minus y1 is equal to La. So give question number 9 and give question number 10. Okay, so length of the element is equal to what? The same what in the previous what you studied in the mathematics, that is length of this element is equal to square root of this x2 minus x1 whole square plus y2 minus y1 whole square. Okay, so give question number 11. Okay, so we know that. Okay, next one is we know that the element stiffness matrix for bar element is k is equal to Ae by L 1 minus 1 minus 1 1. Okay, give question number 12. But we know that the element strain energy for the local coordinate system is equal to uv is equal to half of q dash t k dash q dash. Okay, that is the transport of. Okay, give question number 13. Okay, but we know that ESM is equal to q dash LQ. Okay, substitute this equation 14 equation in number that in 13 we are going to get this equation. Okay, uv is equal to half of LQ dash. Okay, so wherever LQ dash is there, substitute here. So it may be wrong, so 14 should be substituted in 13 equation. Okay, so q dash LQ. Okay, so now after simplification you are going to get half of transpose of q L transpose k dash L, okay, into q. Okay, question number 15. Okay, the strain energy in the global coordinate system can be written as u is equal to strain energy is equal to half of q transpose k q. Okay, give question number 60, where k is nothing but what? Element stiffness matrix for global coordinate system. Okay, compare equation 15 and 16. You are going to get k is equal to transpose of L k dash L. Okay, give question number 17. Okay, so where L is the transformation matrix. Okay, and which is given by this, already we know this. So L is equal to Lm 0 0 0 0 Lm. Okay, transpose of this nothing but what? Lm 0 0 0 0 Lm. Okay, so now but we know that L is equal to cos theta, M is equal to sin theta are the direction cosines, and the stiffness matrix in the local coordinate system which is given by, so this is a bar element, and local this is L transpose of k is equal to Ae by L. So that transpose you have to write this matrix. Okay, transpose is equal to what? Like L M minus L M minus L M L M. Okay, so now we know that k is equal to transpose of L k dash L, which is equal to L nothing but what? This formula. So substitute this, and M nothing but, and this transpose of L k dash Le. So L nothing but what? Normal L is Lm 0 0 0 0 Lm. Okay, Now the stiffness matrix for this element is, so you have to multiply this into this, we are going to get what? K is equal to AE by LE, L square LM minus L square minus LM, okay, LM M square minus LM minus M square, L minus L square minus LM L square LM minus LM minus M square LM M square. Okay, so this is an expression for stiffness matrix for truss element in global coordinate system. Okay, this is most important formula. Okay, you have to remember this formula. How to remember this? It is symmetrics. Okay, just to scratch this. Okay, just to draw one line here. So this is symmetrics. Okay, this is, you have to draw like this. Okay, still observe here, this is and this is symmetrics. Okay, the opposite should be symmetry. L square means here also L square, this is minus LM means minus LM. Okay, so symmetric matrix. Okay, so you can, if you remember first and the last, okay, first and first two box means you have to write as it is in the down opposite in direction. Okay, so like that you have to remember the element stiffness matrix for truss element, that is L square LM LM M square. Okay, and second one is also same, L square LM LM M square. Okay, this is opposite, like this you have to remember. Okay, so outside is same, this is K is equal to AE by L, this is out same, but inside it should be remember. Okay, based on this only you need to calculate the stiffness matrix for truss element. Okay, what I hope you understand this derivation, and this derivation is most important in the point of examination. You have to remember this. Okay, L square LM LM M square. Okay, and minus L minus opposite one more side is you have to put minus 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 minus, same. This is L square LM LM is there. So here LM LM M square M square, just to put sign, opposite is just to put the minus sign. So this you have to write this side, this side you have to write this side. Okay, so this is the derivation of element stiffness matrix for truss element. Okay, I hope you understand this derivation in local and global coordinate system. Okay, truss nothing but what? It is a bar. Okay, it is an engineering structure made up of number of bars connected through a small joint or riveted joint pin, etc. Okay, so this is called as a truss element. So I hope you understand this. This derivation is most important for the point of examination. Okay, thank you.